When Martians descend on England in a novel, The War of the Worlds, published in 1898, they incinerate troublesome humans and lay waste to suburban towns with heat rays that turn all before them into a smoky dance of lurid flames. Such ray guns have been a recurrent feature of science fiction ever since. Despite the efforts of military types, though reality has lagged far behind scientific. In 1934, to no avail, Britain's Air Ministry offered €1,000 to anyone who could use rays of some sort to kill a sheep at a distance of 180 meters. A decade later, a Japanese device that generated microwave managed to snuff out a rabbit that was 30 meters away, but it took 10 minutes to do so. Even the invention of lasers in 1960 failed to usher in the age of directed energy weapon, as ray guns are known in the jargon. Ronald Reagan's effort to weaponize lasers in the Star Wars program of the 1980s was spectacularly unsuccessful. This time, it's different. According to Kelly Hammett, who joined America's Air Force Research Laboratory 27 years ago and now runs its directed energy directorate. From my entire career, he says, we have been working on directed energy. We are finally at the point at which we are going to see systems that will make a more substantive difference on the battlefield. If true, that will change the course of war. At the moment, shooting an object out of the sky generally means firing something expensive at it. If the object is an enemy plane or sophisticated ballistic missile, that is probably worthwhile, but Israel, for example, routinely expends $50,000 interceptors on homemade rockets that cost about $1,000. Disparities like this make it easy and affordable to attempt to overwhelm defenses with missile salvos or drone swarms. Lasers, by contrast, are cheap to fire and never run out of ammunition. Lasers come in many varieties, but two in particular have been the subject of weaponization. These are solid-state lasers and chemical lasers. A solid-state laser works by stimulating the emergence of a laser beam from a crystal or a piece of glass by pumping energy into that solid. The first laser used a ruby as the crystal and a flash lamp as the pump. The power to do this is provided by an electric current. A chemical laser, meanwhile, draws its energy from reactions between two or more substances and uses that energy to pump yet another substance to emit the beam. In the first decade of the current century, America came close to developing a chemical laser weapon. This was a hangover from Star Wars, a megawatt device intended to destroy intercontinental ballistic missile just after they took off. Tests conducted in 2009 were successful, but the system weighed 17 tons and was so longer that it required a Boeing 747 to carry it. Also, the pumping reaction involved chlorine, hydrogen peroxide and potassium hydroxide, all of which are corrosive, as was the substance being pumped, iodine. This is not an ideal mixture to have on board a plane. Having burned through $5 billion over 16 years, the program was therefore cancelled in 2012. Today's laser weapon have by contrast gone down the solid-state routine. As Thomas Carr, have heads the Pentagon's work on directed energy, explains, they use a laser to pump a laser. The main laser's core, the equivalent of the ruby, is doped with an element such as niobium to give it suitable properties. Instead of flash lamp, this laser is stimulated by a laser-emitted diode. By picking the right combination of ingredients from the main laser, its output can be tuned to an optimum wavelength, about 1 micron, that results in a narrow, far-reaching beam resistant to abortion by water vapor in the atmosphere. Water weapon in the atmosphere. Today's solid-state lasers are also much more efficient than their predecessors. A third of the electricity driving them is converted into laser light, compared with just a few percent in earlier generations. Dispensing with gases, moreover, means less plumbing and a more compact design. The breakthrough for solid-state laser came in 2014 with the testing by America's Navy of one that had a power of 30 kilowatts, the output of an average home boiler. When fitted to a small vessel called USS Spons, it's proved able to fry the components and motors of the nearby drones and boats. Spons' captain was then given permission to use it for real. In light of this success, a 60 kilowatt system similarly intended for use will be fitted on USS Spence, USS Preble, a destroyer, later this year, and an even more potent 150 kilowatt weapon is undergoing tests on large ships. Nor are such devices exclusively naval. In February, the American Army said it planned to field its first combat-relevant laser, a 50 kilowatt weapon that would sit auto-striker armored vehicles and defend them against aerial threats by 2022. Military lasers have also benefited from progress in materials science. The heat rays employed by Wells Martians relied on a polished parabolic mirror of unknown composition. destruction. Their real-world successors similarly use mirrors to combine and bounce light within the weapon before sending it out through a window on its way to its target. Since lasers concentrate huge amounts of power into small areas, these mirrors have to be coated with reflective materials that absorb as little energy as possible. Similarly, the coatings windows require high transmission materials that permit as much energy as possible to pass. Both types of coating have come along greatly in the past 20 years because of their use in optical gyroscopes, which are fitted widely in aeroplanes and ships, says Mr. Carr. Another advance has been adaptive optics, a set of techniques that use special sensors and deformable mirrors to compensate in real time for distortions caused by Earth's atmosphere. This technology, which enables military lasers to be aimed accurately, was pioneered in secret laboratories in the 1980s and then declassified in the 1990s, to the considerable delight of astronomers who use it to adjust their telescopes. Last year, the American Air Force Starfire Optical Range in New Mexico approached industry to develop a new and powerful sodium laser, one that energizes the sodium atoms in a layer of the atmosphere called mesosphere to create artificial guide stars. This would refine adaptive optics for both astronomical and military purposes. The next challenge is to soak lasers up still further so they can take aim at large missiles as well as the small ones that the Preble and Striker weapons will be aimed at. The goal, according to Mr. Carr, is to achieve 300 kW by 2022 and 500 kW by 2024. These will be demonstration devices rather than battlefield ready, but a century and a quarter of Welsh vision, it looks as though the ray gun is at last a reality.